started to talk about error correcting codes yesterday. As I said, we'll be only able to do a very brief coverage of this topic. And yesterday I tried to tell you the basic concepts behind linear block codes. We said that there are essentially the two most important kinds of channel coding schemes are the so-called block coding schemes and the convolution coding schemes, out of which we will be very briefly be able to touch the linear block codes. We also saw that channel coding is essentially distinct from source coding. The purpose of source coding is to remove redundancy, whereas the purpose of channel coding is to introduce redundancy in a controlled manner so as to be able to achieve error-free communication, at least as close to error-free communication as feasible. In any case, we worked out certain relationships between the n and k parameters of an nk block code. Right? An nk block code consists of a mapping scheme in which a group of k information bits are coded into a group of n code bits, right? And the relationship between n and k that we saw was the so-called Hamming bound, right? And that Hamming bound requires us to be able to first specify what properties you want from your error correcting codes, and this feature is typically specified by specifying how many errors we would like to be able to detect or correct. Right? So the Hamming bound is defined in terms of three parameters: the value n, the value k, and the value t, where t is the number of errors that you want to be able to correct. Okay. So based on that, we obtain the Hamming bound, which tells us how to choose the third given any two of them.
So
right?
Is n independent of t?
No, all the three are related.
For a given k.
N, k, and t are related to the Hamming bound, right? That's all I can say. So given if for any particular reason you have a reason for choosing two of them to be specific values, then the third will be limited by that, right? And then we introduced the linear block codes through the generator matrix G. In particular, we are considering what we call systematic linear block codes, right? In which the first k bits of the code are precisely the same as the k information bits or data bits that we are encoding. All right, and the next n minus k bits or m bits are called the check bits or parity bits, and they are generated by taking linear combinations of the information bits or data bits, right? And this whole thing is specified by a generator matrix G. For example, this was the example we considered for a 6-3 block code, okay, in which this was the generator matrix G. This is the identity matrix, which tells me that the first 3 bits will be the same as the information bits, and this is what is called the parity check matrix, which specifies the check bits or parity bits in terms of data bits, right? This is an example. If your input sequence input information bit sequence is this, your output coded sequence encoded sequence is this 6-bit sequence, right? When it is this, that is this, and so on. I think this is where we stopped yesterday. So I have done a very quick revision of what we did yesterday. Now, schematically, I can represent this implementation, this generator matrix implementation, like this. Your data is coming in, it's being stored in a some kind of a shift register or something, some memory device, and then basically D1 is being picked up first by this commutator, D2 is being picked up next. This is the first code bit, this is the next code bit, this is the third code bit, and the fourth code bit is obtained by taking linear combination, appropriate linear combination of these bits. The fifth also a different linear combination, sixth also a different linear combination, right? So essentially you generate this and transmit them one after another, right? So this could be a schematic representation for the generation of linear block codes. Okay. To proceed further, let's recapitulate that C, the code word vector, is related to the data vector or the information bit vector D through the linear transformation by G, through the linear transformation G. That is, the vector C is the vector D times G, where C and D are what kind of vectors? Row vectors, not column vectors. If it was column vectors, then it would have been the other way around. Okay. Now, G in turn has a specific structure, right? What is the structure? It consists of, it can be partitioned into two parts: an identity matrix I sub k, where k is the length of your information sequence, and a parity check matrix of size k into n minus k, right? K into m. This is k into k, this is k into m. This is not visible. Okay. On the next sheet, at least you can write this. On the next page, I'll use a different color. I'll return to my normal color, that is purple. Is that fine? Now, so okay, I'll rewrite this just in case you are having problem. C is equal to, this is okay, this is visible. Fine. Now let's take this D inside this. If I multiply this D with I sub k, the identity matrix, I'll get the vector D itself, right? And multiplying with this will give me some vector D times P, which I'll write as, let's say, C sub P. What does this tell me? It tells me very clearly what we have already understood, that the code vector C is comprised of two components, right? The first k bits of the code vector is nothing but the data vector itself, and the next m bits are this is a 1 into m row vector, right? Because this was k into m, P was k into m. This is 1 into k. When you multiply that, you'll get a 1 into m vector. So this is a vector of dimension m, consisting of the so-called parity bits or the check bits, right? That's a structure that comes out also from the structure of G, which you have chosen for a systematic code, right? So for a systematic code, this is the structure of the code. So as far as encoding is concerned, I think we have understood how linear block codes are generated given a specific generator matrix G. Okay. Now let's see. Suppose we want to decode a received sequence which has been generated like this and then transmitted through a noisy channel. Decoding of such coded sequences. For that, we like to first study certain basic properties of the generator matrix. To start with, we may recollect that any binary sequence, when added to itself, exclusive OR with itself, will produce an all zero sequence, right? I'll start from there. Now dp and cp are really the same thing, right? Because c sub p is equal to d multiplied by p. So if I write like this, you'll all agree with this. This will be equal to a vector which is consisting of all zeros, right? M, because c sub p was a vector of length m, okay? Which I can write, this relation again I can write in matrix form.
So what is the operation?
XOR. This is a, when I said linear combination, you were absent yesterday, I think. It's basically we are working in a special field. We are not working in the real field of numbers. We are working in a Galois field of numbers, which are essentially, in this case, binary numbers. Right? The addition operation defined here is the exclusive OR operation, the modulo 2 operation. Right? Modulo 2 addition. So we are working in that number system here. So in matrix form, we can write this as D. This, I'm sorry, I'll have to rewrite it. We know this is our code vector. It consists of D and CP, right? This equation I can rewrite like this: D is being multiplied by the matrix P, right? And CP is being multiplied by the matrix. What is it being multiplied with? Identity matrix. And what is the dimension of this identity matrix? Not K by K. It's M by M, because this is a vector of dimension 1 into n, right? And this results in a m-dimensional row vector 0, right? So I'm just rewriting this equation in a matrix form. Not very clear. It's just matrix multiplication. Is this clear? This equation is okay. Now I'm just writing this equivalently as equal to this, because if I do a block multiplication of this vector and this matrix, I'll get the same equation again. D into P plus Cp into Im, which is Cp, is equal to 0. You're taking a row vector multiplying by a column matrix on a block by block basis. Okay, simple matrix multiplication, really nothing else. Okay, now this matrix also has a very important purpose to serve, as you can easily appreciate, and therefore it has got a special notation for itself. It's denoted usually by H transpose. Okay, this matrix is usually denoted by H transpose. What is D into D along with Cp? This is the code vector C, right? Yeah. It consists of your information bits followed by check bits. So what we are saying is that every code vector C, which is generated by this data matrix G, satisfies this equation, right? In other words, the equation that we are really talking about is C multiplied with H transpose is equal to 0, right? Where H transpose is this matrix, and it is defined to be the parity check matrix. And the reason why it is so called is quite obvious now. Is it obvious? The way it works is, or the way it helps us is, if you are given a specific sequence, right? If you multiply it with H transpose, if the result is 0, then you know that that given sequence was a valid code word generated by that matrix G. On the other hand, if it doesn't produce a 0 vector here, that means it is not a valid code sequence. Okay, that's why the matrix H is called a parity check matrix, because it is able to tell me whether the parity bits and the data bits that are coming along, they bear the same kind of relationship with respect to each other, which is implied by the structure of the G matrix, right? It's a check on the structure of the G matrix, and therefore we call it a parity check matrix. And this forms our basic clue to decoding. Right? Of course, when we are trying to decode a received sequence, that received sequence may or may not be a valid code word, because if errors have taken place at the receiver due to channel noise and various other reasons, at the moment, of course, we are only talking about channel noise, we will have a received sequence R, which is not going to be C, but associated with some, let's say, error pattern E, right? For example, the error pattern may contain all zeros except a single one somewhere. That will correspond to an error at that specific bit location. Suppose the first bit of this error pattern is 1 and the rest are all 0, right? That means the first bit has been erroneously decoded in the received sequence. I mean, the received sequence contains the first bit to be erroneous, right? For a different error pattern, we will have a different received sequence. So you might have transmitted C, but at the output of your, let's say, match filter receiver, after your thresholding, you are getting a sequence R, which is different from C, right? And this is what now the decoder has to do. It has to take in this input sequence and hopefully take you back to C, so that there are no errors, right? That is a function of the decoder. That's what a decoder is required to do. So this is your received sequence. What are the dimensions of vectors C and E? Both are n-dimensional vectors. C is an n-dimensional code vector, E is an n-dimensional error vector, most of which we expect to be zeros. In fact, if there is no error, then E is perfectly zero. It is consisting only of 0 bits. I mean, bits, all bits being equal to 0. For example, if D, for the same 6-3 code that we are considering, let's say the data bits were 100 and the corresponding code word you can check that will come out is this from that generator matrix, which we were considering a few minutes ago, right? If you take this as a generator matrix, if you feed this as a data vector, input vector, the code vector that will come out is this, okay? And maybe your received sequence is this instead of what you transmitted, right? When I say received, we are really talking about the output of your threshold device at the receiver, because it is there that the decoder will be fitted. So what is the error pattern associated with this received sequence? 0 0 1 0 0 0. That's your E. Okay. So you understood that. All right. Now, yes. Yes.
How are we able to decide which row to match it with?
So we are coming to that. I have not yet given you the decoding procedure. I have to still. I'm only trying to tell you that the received sequence can be modeled as the sum of the actual code sequence that you transmitted and an appropriate error sequence, right? Depending on how many errors have taken place where, right? That's all I have said so far. Now let's say C sub I is the actually transmitted code word. And let's say E sub I is the corresponding error word that you get. Okay. If E sub I is 0, of course there is no error. And we have already seen that R sub I, the corresponding received sequence, is C sub I plus E sub I. Okay. And if you compute RH transpose, and if it turns out to be 0, that will imply that E sub I is 0, right? In general, it will not turn out to be 0. It will turn out to be some non-zero vector, right? Instead of getting a vector of zeros, m zeros, we will get a vector of an m-dimensional vector of zeros and ones, right? In general, if it is not 0, it has m components. Some of them will be 0, some of them will be 1s, right? That's the most general expected situation. Precisely speaking, this S will be the vector S that you will get. You can again write C plus EI into H transpose, but CH transpose is 0, right? So it's nothing but EI H transpose. Okay, I am writing S equal to RH transpose. R is Ci plus Ei. I should probably write SRI, write this as Si, right? Let me, okay, is it okay? So this kind of might give you the feeling that there exists a mapping between this S that you can compute from your given R. You have received the sequence R sub I, right, from which you can compute S sub I by multiplying with H transpose, right. So it might give you the impression that given this S sub I, which I can compute from the received sequence, I should be able to obtain E sub I, right, because there seems to be a linear relationship between these two, right. And once I have the E sub I know my transmitted code word, because I know where the errors have taken place, and therefore I can correct those errors, right. But things are not that easy, as we'll try to appreciate. The reason is this equation E sub I H transpose. Can you give me the reason? What is the difficulty? This equation does not have a unique solution. Okay. And can you appreciate the reason why it is not a unique solution? The reason is as follows. Corresponding to every C that you might have transmitted, listen to this carefully, corresponding to any C that you might have transmitted, you can always think of some other code word and some other EI, some other corresponding error pattern, which would have produced the same received sequence, and therefore would have produced the same syndrome. Incidentally, this vector S sub I think I forgot to mention this, is called the syndrome vector. Or simply the syndrome. Okay. So do you appreciate that? That given a particular syndrome vector, it may not be easy to go from there to E sub I, because I can produce a different E sub I corresponding to I may get a different there may be many different E sub I's which will produce the same syndrome, corresponding to the fact that for each code word I can identify a different E sub I which will produce the same R.
So, but if we work under the assumption that we have some maximum number of error bits, then we'll get a unique solution.
That's right. So we'll come to that, right? But by itself, it doesn't contain.
So if we consider that the maximum number of error bits is some less than a particular number, then we'll get a unique solution.
Not only that, we like to what
H.
we like to do is
Structure of H should be such that it is not.
no matter what structure of H you might have, this fact is not related to structure of H. This fact is related to the fact that Si has been generated from what? From R sub I, right? If I have a given R sub I, S sub I is fixed. There is no confusion about that, right? Because S sub that is being generated like this. But I could get this R sub I by different combinations of code words and error patterns. You might have transmitted a specific code word, but at the receiver I don't know what you transmitted. So I can think as if some other code word was transmitted and if some other error pattern was associated with it to give me the specific R sub I that I have obtained.
So what wasn't this the problem that we were trying to eliminate by putting the parity check? Because we assumed that they were less than T.
Yes, sir. Then we'll get a unique solution.
Yeah. So the uniqueness will come by imposing some other. But have you understood this point? I'm coming to your point in a few minutes. But is this point all clear that this does not contain a unique solution? Right? This equation does not have a unique solution. Is this point understood? Right? From then I can proceed on and come to the points that you are making.
We have to see in which sphere does it lie in.
Yes, but at the moment I have gone away from the sphere interpretation. But yes, basically that's what you have to do. Yes.
Does the demodulator note
Decoder.
Decoder, not demodeler.
Decoder.
Right, because demodulation has already been done. We have already got R sub I, which is a binary sequence.
Okay.
Right.
Does a decoder know P?
Yes.
Yes, of course. It has to. It has to know H. And to know H, it has to know P.
That's what I'm asking.
How will I know? Communication system is hopefully being designed by a specific set of individuals who are designing both transmitter as well as a receiver. Okay, so they know what they are doing. Okay, so that's easy. That's easy. That's part of when you design an encoder. There is a specific decoder structure also implied. Okay, that's right. You can't have an arbitrary decoder when if you don't without knowing what your coder was, right? Somebody has used a cyclic code and you trying to decode it in a different way, which is not at all relevant to cyclic codes. They're obviously doing something wrong. Okay. So the parity check matrix is known to the decoder. All right. So the point is that there are 2 to the power k code words. They can be 2 to the power k solutions to this equation. Let me illustrate by again an example. Let me take an example. I think you have understood this point, isn't it? That there are 2 to the power k different possible solutions, right? You understood this point because
there are multiple solutions, that is clear, but how it will be able to do
because for every valid code word I can think of an error sequence which would produce that given R sub I, isn't it?
Now we have to.
And therefore it would have produced that specific syndrome that has been produced. That's the only answer. For every specific code word, and how many code words are there? 2 to the power k. I can find some error sequence such that that code word plus that error sequence will produce that specific received sequence that I have got, right? And therefore it will produce that same syndrome because the received sequence is same correspondingly. All right. Now let me give you an example. Let's take d equal to 100. Again, that example is in the context of the same 6-3 code that we have been talking about. C corresponding C is 100, 101, and we said R was 101, 101, and the actual error pattern is 001, 000. Okay, this is the actual error pattern corresponding to this situation. Consider C equal to 101. That is when the data sequence is not 100, but data sequence is 101. Then the corresponding code word will turn out to be this, right? And it is very easy for you to check that if I take E like this, then I'll get the same R. Okay? Or, isn't it? This is 101 as such, and 110 added to 011 gives rise to 101. Similarly, if I take the code word 010, 011, right, and the error pattern 111110, I'll again get the same received sequence R. You add these two, you'll get the same R. In fact, it is true for every possible valid code word, right? And the answer also now we know what we should do. Here is a situation where there is a single error. Here is a situation where there are 2 errors. Here is a situation where 5 errors. Which is the one which is most likely to be the case? The single error case. So the answer is find the solution for the error pattern which is associated with the least weight, least Hamming weight. Hamming weight is defined to be the number of ones in a sequence, right? which has the least Hamming weight.
Will that be unique?
There will be some least.
Yeah,
Okay.
some least.
So that least is what you have to check.
4 or 5 options.
I mean, a few least.
Yeah.
Then
If you have that choice, then of course you can't do much. You can choose any one of them arbitrarily. But usually that, no, theoretically there is a possibility of that happening.
So under the assumption we won't have.
No, that's not possible because
that's what real actually is.
no, it's possible. It will not be possible if your code is properly designed. If you have located your code words sufficiently far apart, that is, it takes a large number of errors to go from one code word to another code word, right? If your code words are properly designed, that will never happen. In fact, that's what we discussed last time.
But even then, supposing it takes only 2 Hamming distances, to go from one code.
You are forgetting our discussion yesterday and the time before that, where we did a geometrical picturization of this code book design, where we said that if you want to design the code book, it should design in such a way that around every code word, if you want to correct up to t errors, then you have to have the Hamming spheres of radius t around each code word to be non-overlapping with respect to with each other, right? If you have that kind of situation, you will always have one unique solution, right? Because corresponding to one error, there will be only one code word which is nearest to it, right? And basically that's what you are saying. We are finding that code word which is nearest to it, which is associated with the least error.
So we have to assume
Right.
that we cannot correct more than t errors.
That's right.
On that basis, we have to do it.
No, here even that doesn't come to the picture. Here the only thing that is coming to the picture is choose the error sequence which kind of implies minimum number of errors,
Minimum number of errors.
right? Because it's smaller number of errors is more likely to happen than a larger number of errors, but in a normal channel. Therefore, you give more weightage to this possibility than to this possibility or this possibility. Mind you, this is possible. It's not that this event is not possible. It's possible that you actually transmitted this and you received, sorry, you actually transmitted this and you received this, and therefore 2 errors took place, right? But there is no, the point is the possibility of that event is less than that you transmitted this and received this.
So I'm not clear about one thing. Like in the first case, the error is only in one bit position, the third bit position.
It doesn't matter where.
No, fine.
Right.
If it is, we can construct 2 possible solutions by putting that single error into 2 places. Let's say right now it's in the third place, and we could have another error, another solution with the error in the first error bit in the first one.
No, that will imply a different received sequence. That will imply a different received sequence. If you transmit this and your error pattern is 1 0 0 0 0 0, then your corresponding received sequence will be different. What is your confusion? Can you specify your confusion? Let me go over it again.
We have to assume
The number
it is
of-
separated by t, 2t plus 1.
So the number of ones that should be there in a E vector which has to be chosen should be less than t.
Yes, sir.
The number of ones should be less than
Yes,
t.
yes, that is implied, of course.
So that's how we should choose this E.
No. You see, the t may be a large number, and you may have several solutions less than t. Then what do you say?
Out of those, the minimum.
Then why do you have to go through a 2-step procedure?
Maybe there are several
Right?
solutions. This means
You might as well choose straight away the situation which corresponds to minimum. We are of course saying that that minimum should be less than t,
Less than t.
right? But that's secondary.
So, but
That's
the
second
code
one.
is properly designed.
Then
Then
For
for all,
less than t
One,
also it will
one
be
at a time,
a unique
please.
solution.
so for all less than t, it will be the same sphere center. So center will,
Yes, but within that sphere,
there will be many.
there can be many error patterns with one error.
So the point is this, if
Yes,
it
sir.
is
Sure.
But they will give a different receipt.
But they will correspond to different received sequences,
Yes, sir.
isn't it? There can be many error patterns corresponding to a given transmitted code word, resulting in different received sequences. But for a received sequence, there is only one unique way by which you can go from there to its nearest code word.
minimum one.
Right?
Yeah, the minimum number of ones.
That's
Essentially, you're just saying that if the error corresponds, error as valid for a particular code, the least is greater than t, that means it does not belong to that code word at all.
Anyway,
Still, that is secondary now. Minimum.
that situation is hypothetical. It's not worth discussing. What is you're saying that because you'll never have a least which is greater than t, right? The least will have to be less than t.
I mean, because if it is greater than t, it means it doesn't belong to that particular.
Least has to be less than t.
No.
Least has to be less than t.
The question is, you can please listen to me. For a given received sequence, I can construct error patterns containing single errors, containing double errors, containing triple errors, and so on and so forth. Right? Is it clear? Now, for a given syndrome, you find out which are the possible error patterns.
The minimum number of
Right? Maybe you get one error pattern of a single error, and one error pattern of a double error, one error pattern of a triple error. Then you choose a single error one. That's all we are saying. Nothing more than that.
less than t we don't have to say because it will always less than the minimum
Right.
one will be less than t.
Obviously. Yes. Is what always non-zero?
No, if there is no error,
No, it may be zero.
Or it could be
In that case, we'll get a syndrome to be all zero. That's all. Right? And then we know that we are fine. We don't have to do any correction. Right? If we get the syndrome vector to be all zero, then we are there. No further effort is required. Alright. So basically what we are saying is use majority logic decoding. Right? Essentially it boils down to that. That is, find the code word which is nearest to the received sequence. Basically that's what you are saying. Alright. Therefore what we really do is, for decoding, you construct a decoding table. See, there is a further problem here. How many different error patterns I can generate? 2 to the power n, right? Obviously, because that's why I have to put a limit. I can't correct all these error patterns, right? Every code will have a limit up to which it can correct, depending on how it is designed, depending on what is the minimum distance between code words. This was a crucial parameter we discussed. If you want to correct up to t errors, what is the required minimum distance between the code words? 2t plus 1, right? Every code word must be 2t plus 1 away from the other code words, from every other code word. Now, therefore, I cannot possibly hope to be able to correct any kind of error pattern that might take place, right? That also can be appreciated from the fact that the vector s, what is the dimension of the vector s? Its dimension is m. M is n minus k. What is the number of different possible syndromes I can have? 2 to the power m, 2 to the power n minus k. So the maximum number of error patterns that I can correct are 2 to the power n minus k, right? The syndrome vector has a dimension of m. The vector s, this vector has a dimension m, because this is a 1 into k vector, this is k into m matrix, this is 1 into m. M is the number of check bits, right? So the dimension of the vector s sub I or s is m, where m is the number of check bits. So the number of different patterns, syndrome patterns I can have is 2 to the power m, right? Therefore, if I want a unique decoding procedure, that is for one syndrome vector, one unique error pattern associated with it, then how many error patterns I can possibly take care of? Only 2 to the power m, one corresponding to each different syndrome vector, right? Therefore, the procedure consists of going through a mapping or a table construction in which with every possible syndrome vector you associate a corresponding error vector, right? And obviously the error vector should be such that find the minimum weight error vector corresponding to that syndrome. right? So, and the best way to do it is, so for example, let's take the same example, 6-3 code. What is the value of M? 3. How many different syndrome patterns I can generate? 8. Right? Now therefore I can take care of only 8 error patterns, whatever they might be. And I have decided that I will give more weightage to error patterns with single errors. Then maybe if I have error correction possibility even beyond that, then I can take care of double errors and so on, right? So what I'll do therefore is I'll list out first all zero error patterns that corresponds of course to the syndrome all 0. That is trivial. Then I list out all error patterns with single error, right? Start with 1 0 0 0 0 0. Compute what is the corresponding implied syndrome. How will you compute that? EH transpose, right? 1 0 1, right? Then take the next single error pattern. This will turn out to be this. Then you take the next one, right? This will turn out to be this. Next one turns out to be 0 1 0. Next one turns out to be 0 0 1. Sorry, I think I made some mistake. 1 0 1 0 1 1. This is 1 0 0 here. No. This was okay. I'm sorry for this. This is 1 0 0. And this was 0 1 0. Okay. And you're left with one more. This gives you 0 0 1. How many patterns I have exhausted? 7. There is one more pattern left. So if you want, I can take care of one error pattern with 2 errors, right? Maybe this one. You'll have to find out which error pattern of 2 errors will produce this syndrome. It turns out to be this. Okay. So now I have a decoding table. I look at the syndrome, find the minimum weight error pattern from here, add that error pattern to the received word, and I have my decoded sequence. Is the procedure clear? So you will have the received sequence coming in, that's operated by the parity check matrix to generate the syndrome, and then the syndrome output vector maybe is given to a lookup table in a ROM or something to produce the output coded output code sequence, error pattern sequence from which you can construct the code sequence. You could as well have the code sequence outputted. This is not. Okay, what is the storage required here? You require to store how many patterns in this table? 2 to the power n minus k, each with how many bits? N plus n minus k, right? 2n minus k bits. This is the required size of the ROM that you restricted. Okay, you require to store 2 to the power n minus k words, each of length 2n minus k bits.
To store this S or the entire.
To store this table, right? So that if you address the ROM using this address, you will get this output sequence, to which you can add your received sequence and get your code sequence. Now we have only 5 minutes, but I can briefly discuss one thing about how do you choose, because we are not really going to design of codes. As I said, that is a full-fledged subject by itself, but I like to offer a few comments. How do you choose the entries of the G matrix or the entries of the H matrix such that we are able to correct all the single errors, right? How do you really do that? Now that's not an easy job. That's quite there's really no systematic way of designing generator matrices like that. But for a specific kind of codes, which are called Hamming codes, Hamming single error correcting codes, it's relatively easy to do this design. And I'll just like to go over that for you. Are you familiar with the Hamming code in some other context, in any of your other courses? No. Okay, so we'll discuss briefly the Hamming 7-4 single error correcting code. Okay.
One thing I missed that. The table which you constructed, you
Yes.
actually multiplied it by each transpose and got the value.
That's right. Each of these error parent sequences multiplied with H transpose, that is the entry here.
Okay. And one more thing, H transpose was P and I, right?
Oh.
P was of the dimension K by M and I was of the dimension K by K.
This is H matrix, H transpose. This is M by M, and this is M into, sorry, this will be K by M. No, how can it be K by K? Right? This is what I try to clarify right at that stage. This is how we got this H matrix, right? Let's go through each dimension in case there is a confusion. This is 1 into K, this is 1 into M. This whole thing becomes 1 into N, right? Now, since this is 1 into K, this matrix has to be K into M, right? And this matrix, this CP is being multiplied by IM, which has to be an identity matrix of dimension M into M. Is it clear?
The single error can be corrected using adding 3 bits only.
Yeah, let me.
Why we are adding 4 bits?
No, 3, 7, 4.
The Hamming bound is satisfied exactly for 7-4, not 7-3. Okay, this 7-4 comes from the Hamming bound. It turns out that the two sides will precisely be equal if you take n equal to 7 and k equal to 4, and for t equal to 1, right? You can substitute it and find out, right? So you can't do it with k equal to with n equal to 6. This is what you are saying, isn't it? And
No, sir, I was saying that if it is 7-3, then also we can correct only.
what is 3 here? K. Yeah, but I'm doing something better than that, isn't it?
Yeah, better.
All right. All right. You give me a few minutes more. As I said, you can easily verify that it satisfies the Hamming bound exactly. Please check. Okay. Now, what is the value of M? It is 3. 3 check bits are implied in a 7-4 code, which implies how many non-zero syndromes? Total is 8, out of which 7 are non-zero, right? So 7 non-zero syndromes. Okay. What is the value of n? 7. How many error patterns are there with exactly a single error? 7 error patterns?
6.
Why 6? The code is of length 7. You can have an error at each point, each location, right? Separately. So there are exactly 7 error patterns with single errors. Okay. So we can correct, it seems to be possible to associate every syndrome sequence with a corresponding error pattern sequence of different kind but corresponding to a single error, provided we choose our H matrix or G matrix properly, right. It's the possibility is there because we have exactly 7 syndrome sequences and exactly 7 single error pattern sequences. The question is how to do it. So it seems to be possible to correct all single error sequences, all single error patterns. And of course no more than that, because we don't have any syndromes left after that. Let's consider the situation in the error sequence is 1 0 0 0 0 0. What will be your S equal to EH transpose? What will it correspond to? It will be nothing but the first row of H transpose, isn't it? Is it clear? All right, one more. It's fine. It's nothing but the first row of H transpose, not column, because syndrome sequence is an m-dimensional vector. It cannot be the column. Column is an n-dimensional vector. All right. Similarly, if I take the sequence E equal to 0 1 0 0 0 0 0, what will be S? Again it will be second row now, right? Therefore, what does it mean? If I want all these 7 syndrome sequences to be associated with 7 different error patterns, 7 distinct error patterns, then all I have to ensure is that all the different 7 rows of H transpose should be distinct, right? Is it clear? If I want each of these syndrome patterns to be associated with different distinct single error patterns, then the way to ensure that is that these H matrix rows should be all distinct, because that's what I will get as syndromes. If for 1 0 0 0 I get a syndrome sequence, for 0 1 0 0 0 I should get a different syndrome sequence which is lying in the next row of H transpose. For the next third error I should get a different syndrome sequence which lies in the third row, and so on and so forth. So if all the rows of H transpose are different, I am guaranteed a 1-to-1 mapping between each of the singular patterns and a corresponding syndrome sequence. Clear? And that's very easy to do, because we can construct exactly 7 non-zero sequences with 3 bits. M is equal to 3, so all I have to do is put them in any order I like, except to ensure that the lowest part has to be identity matrix. That's all. So that's the generation of a Hamming code. So for unique decodability, all 7 syndromes corresponding to 7 single error patterns should be distinct. This is the point. And the only way to do that is to make sure that H transpose contains all distinct rows. Okay. So one possibility of choosing H transpose is possibly like this. We know the top part of it is P and the lower part of it is I sub M. So the lower part is specified to be 1 0 0 0 1 0 0 0 1. This is specified, right? as far as the top part is concerned, there are only 4 other non-zero sequences. You can put them in any order you like, right? Maybe 1 1 1, 1 1 0, 1 0 1, and 0 1 1. Okay. All right. So that's a Hamming code for you. Corresponding G will be constructed by like this. That will turn out to be and P, you know, it's 1 1 1, 1 1 0, 1 0 1, 0 1 1. Fine. So you have the generator matrix. You have the generator matrix and you can generate the code at the transmitter. So the generator matrix and the check matrix are closely linked by virtue of their design, right? So without, if you don't know at the decoder what the check matrix is, then that means you're not working as on a single corresponding encoder decoder pairs. Okay, I think with that we'll you can generalize this to other single error correcting Hamming codes, not necessarily 7/4, but for arbitrary values of k and n, right? In fact, the same procedure can be repeated. So for Hamming codes, single error correcting codes of this kind, there is really no problem in design. But in general, to design codes with specific number of error correcting capability is a non-trivial job and is a subject of a full-fledged course in coding theory. I think this is a good point at which we can stop.